In this lesson, we want to use the expression for steady-state conditions as a means to derive an expression relating substrate affinity and catalytic rate to the rate of product formation. Keep in mind, theory is fine, but we need our expression to include terms whose value we can readily measure in the lab. Let me just remind you of the steady-state conditions we've specified, where the rate of ES formation is equal to the rate of ES breakdown. Let's begin with the expression for equivalence or steady state derived in our last lesson. Keep in mind that at any time the enzyme might be in either the free or unbound form or in the ES complex. The amount of free enzyme, or E present, will therefore simply be the total amount of enzyme added minus the amount actually bound to substrate. Let's take this relationship and substitute it into our steady-state equation at the top of the slide. This gives us the expression at the bottom of the slide. To simplify our expression, let's rearrange the equation and collect all of the rate constants together. When we do so, we get a ratio of rate constants as shown here. This ratio of rate constants is the Km, or Michaelis constant, an equilibrium dissociation constant. We've simplified our equation since we now have one constant instead of 3. If we rearrange our equation slightly, we get the form in the center of the slide, an expression for the concentration of ES. In the early stages of reaction, product formation depends only on the rate of ES conversion. In other words, velocity is equal to K2 times the concentration of ES. If we substitute our expression for ES concentration, we have equation 1 at the bottom of the slide. Let's remind ourselves that we are operating under steady-state conditions, that the concentration of substrate is so high that all of the enzyme molecules are bound to substrate. This means that the concentration of ES is simply equal to the total concentration of enzyme, or concentration of E sub T. Under these conditions, we are at zero-order kinetics, and the velocity has reached its maximum value. V0 is equal to Vmax. Next, we'll substitute this expression into equation 1, and this gives us the final form of the Michaelis-Menten equation. It tells us that the initial velocity of the reaction, or V0, is directly dependent on Vmax, on how fast the enzyme converts substrate to product. It is also inversely related to Km, so that as Km decreases and substrate affinity increases, we get more product per unit time. Let's now consider a special case where the substrate concentration is equal to the value of Km. Under these conditions, our velocity expression simplifies to 1/2 Vmax. In other words, the Km is simply the substrate concentration, where velocity is at half its maximum value. We can therefore estimate Vmax and Km from our substrate saturation plot shown here. The Vmax would be the asymptote to the flat area of the curve. To find Km, we first find the value for 1/2 Vmax on the y-axis and see where that crosses the curve. The corresponding value on the x-axis is the value for Km. Please note that this is at best an estimate. That is to say, it isn't very accurate. The most important thing to take from this lesson is an understanding of how the Michaelis-Menten equation relates reaction velocity to the two parameters, the maximum enzyme speed and the affinity for substrate.